Okay, in Chapter 3, what we're going to do is focus on some of the similar ideas that we've been dealing with, but we're going to deal with a different type of function now. So instead of our focus being on polynomial functions and the applications and algebra that goes along with them and the geometry as well, okay, we're going to be doing the same kind of thing with exponential functions. So just like they looked in algebra and algebra 2, an exponential function is of the form a times b to the x. Okay, so a couple things about a and b. Number one, a needs to be non-zero. Think about why if a were 0, would there even be a function at that point besides f of x equals 0? Okay, so a can't be 0. And then b has to be positive, so we have to have a positive base, we call it, and they use b for a reason, for base. And as long as b does not equal 1 as well, we don't want it to equal 1, because if it did equal 1, then no matter what we put in for x, the answer would just be still 1. So the answer would simply just be a. So that really wouldn't be an exponential function either. That would be a line also. And ultimately the a here is also what we call the initial value. It's the initial value because if we were to plug a 0 in for x, okay, no matter what the b was, if we plug a 0 in for x, we're going to get b to the 0, which is 1, which would leave us with a. So not only is it the initial value, but on the graph, wouldn't a also be the y-intercept? Because if we plug a 0 in for x, we'd get the answer a. So 0a would be a point on this curve. Okay. Now, a couple things that we want to do first here, and the first two examples I have are from your book. So I'm going to look at page 277. We're going to start with identifying some exponential functions. This first one is an exponential function. The initial value, the a if you will, would be 1. The base would be 3. Whatever is being raised to that power is going to be our base. If you look at the next one, we have 6x to the negative 4. So 6x to the negative 4th is not an exponential function, because you'll notice the difference is that we do have a number out in front that would seemingly be like our a, okay? But the x, the variable, okay, is the base this time. So the key is the exponential function needs to have a constant base, variable exponent. We have the opposite here in choice B. Okay, we have a variable base and we have a constant exponent. Okay, that's why that is not an exponential function. That would be a power function like we studied earlier. C would be, yes, that would be exponential because it's got negative 2 would be our a, 1.5 is our base, x being the exponent again. Okay. If we look at D, this one is also an exponential function. Notice the one difference we have here is that the exponent is a negative x. Okay. But that also qualifies because we could rewrite the 2 to the negative x as 2 to the negative 1 times x. And remember, 2 to the negative 1 by our powers of exponents is 1/2. So we could rewrite that as 1/2 to the x. Okay. So that would qualify because we could put it in that form, a times b to the x. And finally, letter E is a no. Okay. It's not an exponential function because we don't have any variables in it. Okay. The variable, we have a constant base and we have a constant exponent, which means that if we just multiply that out, it would just be a number. That would be a horizontal line. So that doesn't qualify as an exponential. It's just a horizontal line. Okay. Questions so far on identifying? All right. The next thing I want to look at is computing exponential function values. Okay. Just to make sure we're clear on a couple things here. If we were to take us exponential function 2 to the x, got an a of 1 and a b of 2. And we were asked to evaluate f of 4. Okay. Means all we're going to do is just put a 4 into that. 2 to the 4th power, of course, is 16. Okay. If we were to put a 0 into that, we would get the initial value, which is 1. And that would happen no matter what the base is. If we were to put a negative value in there, remember what negative values do for us when they're in the exponent. Negative means that we're going to put it on the bottom and make it positive. Remember our rules of exponents. And so therefore f of negative 3 would be 1 over 2 to the 3, or in other words 1 over 8. Okay? And again, unless they tell you to do so, there's no good reason to change that to a decimal, even though they did on this particular example. Okay, so just leave that as 1/8, and that'll do it. And the other part I want to look at is make sure if we end up with a fraction as our exponent, to remind us what fractions mean with exponents. If I have 2 to the 1/2, that's the same as the square root of 2. And once again, there's no reason to change that to a decimal unless it tells you to do so. Okay? So we could get any kind of number could go into our exponent for x, and we need to be able to handle that. One more to look at, just a reminder of what if we have a negative fraction. So 2 parts to consider. The first part I would consider is that we need to make it positive by putting it on the bottom. Okay? And then from there, we can change it to this exponent form, or radical form, I should say. And remember, when we have a fraction power, the top is the power, the bottom is the radical. Okay, so top is power, bottom is root, therefore it's square root, and 2 cubed, so therefore we get the square root of 8 on the bottom. And once again, no need to put it in this form unless they tell you to do so. Okay, 1 over the square root of 8 would be perfect. Okay. All right, questions so far? All right, let's take a look at another skill that we're going to be asked to do here today is to find a formula for a function with a table given. So if we're given a table of values, okay, and we recognize that it's exponential, and the way we recognize that it's exponential is we look at the y-coordinates and we can see that there's a common ratio between each of the terms. Okay, in other words, if I were to take any given term and I multiply by a certain number, okay, that same number works to get from any term to any term. Okay, of course, going by ones over here on the left. Okay, so if I see that pattern, okay, in this case, multiplying by a quarter gets me from term to term. In this case, multiplying by 3 gets me from term to term. Okay, anytime that we have that pattern in our y values, that's going to be an exponential function. Okay, and the good news is that r, okay, that common ratio that I mentioned, the 3 in this case, or the quarter in this case, okay, that's our base. Okay, that number is going to be our base. So if we recognize that there's a pattern such that the y-coordinates are being multiplied to get from one to another by the same number, okay, it's exponential, and that particular number is our base. Okay. Now the other thing that we have here in this chart that we can see is this. We have 0, 4. That's the y-intercept. True? So if that's the y-intercept, then that also tells us what our a value is. Okay. Over here it's going to be 0, 8. So we're going to have 8 as our a value in that one. And so ultimately that allows us to find the formulas for g and for h in this case. So we know they're exponential. Okay. Since g of 0 is 4, as I mentioned, that means our a value is 4. Okay. And we know that our base is 3. Okay. So therefore our exponential function we'd write, all we need to have our a and b. Just like a line, all we need is a slope and a y-intercept. For an exponential function, we need an a and a b. We need an initial value, and we need a base. So that would be the equation that would give us the values that we saw in the previous chart. And similarly with h, our a value is 8, and our b value is 1/4. So we'd write h of x equals 8 times a quarter to the x. Okay. Now, could you, once you wrote those equations, could you go back and double check and make sure that by plugging these numbers in, that you do get all those same numbers with the answer that you gave? Absolutely. Okay. Take these numbers and plug them in. You can use your calculator to do that, or in most cases it should be easy enough to do by hand. Okay. Okay. Questions so far? All right, so a couple properties about exponential functions. We generally have 2 different types that we deal with. One is a growth function and one is a decay function. Okay. And ultimately, the key elements are here. So if we have a greater than 0 and b is greater than 1, the function is increasing, and we call that an exponential growth function. So when we have a base that's greater than 1, okay, and again, keep in mind it's got to be of this form. If the base is greater than 1, then we're going to have an exponential growth function, and we call b the growth factor. Now, if we have a greater than 0 and b less than 1, okay, then we know that this function is going to be decreasing, and we call it an exponential decay function, and b is what we call the decay factor. Okay. So if we were to have a number in here like 1/2, okay, or 3/4, something less than 1, then we would expect that we would get a decay function when we draw its graph. Okay. So I want to look at on page 279. Okay. You have on the bottom of the page there is an exploration in the blue box. They want us to take a look at some graphs here. We're going to do some comparing of graphs so that we know when we see a certain type of equation what the graph should look like. Okay, we know that one of these functions is our parent function. We'll talk about that in a minute. But I'm going to go ahead and put in the equations they ask us to look at. For part A, they said do 2 to the x. So if I put in 2 to the x, and the window they ask us to use in this one is negative 2 to 2. And then we'll negative 1 to 6. So we're going to go negative 1 to 6 in the y direction. And we'll go ahead and knit graph, and we'll see what we see here. So here's the shape of our 2 to the x function. Okay. Again, it's an exponential growth function. And the next one they ask us to look at is 3 to the x. So let's compare if we change the base to 3 to the x, what difference is that going to make? Okay. They both still go through 0, 1. Okay, 3 to the x is going to grow faster than 2 to the x because the base is bigger. If we were to plot points, the numbers would get bigger quicker in y-coordinates. Also, you'll notice that on the left-hand side, the 3 to the x was below the 2 to the x. Okay, because ultimately we're going to have a situation, if we put a negative power in there, we're going to have 1 over 3 to the something, or 1 over 2 to the something, okay, which is going to give us small numbers, numbers that are going to get closer to 0. Okay, we can see that both are going to have a horizontal asymptote going to the left of y equals 0. Okay, they both get infinitely close to 0, never equal 0. Okay, but we should expect that the 3 to the x should be lower than the 2 to the x on the left side, okay, because ultimately we're getting bigger numbers on the bottom of a fraction. Okay. They asked us to look at 4 to the x, so what should we expect if I put 4 to the x in here? On the right-hand side, it should grow faster or slower? Should be faster. Should be underneath on the left-hand side. A little tougher to see with this window. But as we see 4 to the x, and then we do 5 to the x, you can see that if we increase that base, okay, the exponential function is going to grow faster. Okay? It's going to be steeper, closer to the y-axis, if you will. Okay? Couple of questions that are posed there. It says, what point is common to all these? Well, we can see that they all go through 0, 1. And that's because if we put any base to the 0, we get 1. So they should all have 0, 1 in common. And then analysis here, domain and range. Domain for all these. Okay, we go infinitely far to the left, infinitely far to the right. So the domain here would be negative infinity to infinity. And as I mentioned, no matter what power we put into any of those, we're going to get close to 0 as we go to left, but we're not going to get to 0. So the range should be 0 to infinity, because we're going infinitely far in the up direction, if you will. But when we're going down, we don't go any lower than 0 for this function. Okay, increasing. Increasing, these functions are always increasing. So we'd say they're increasing on negative infinity to infinity. Decreasing, they're never decreasing. Continuity, okay, there are no asymptotes or holes in these types of functions, so continuous, always, negative infinity to infinity, okay, in the entire domain. Okay. Symmetry, there does not appear to be symmetry across the y-axis, so they are not even functions. Okay. They don't go through the origin, and there's no symmetry. There's no other parts that are going to be symmetric about the origin, so they're not odd functions either. So neither even nor odd, so no symmetries. Boundedness, okay, these continue to grow forever in that direction. They are bounded on the bottom, though, by y equals 0. Okay. Extrema, there are no local maximums or minimums. There's no asymptotes. And then end behavior, if we had to write a statement about end behavior here, we would write the limit as f of x, or limit of f of x as x approaches infinity. Okay, as x approaches infinity, what are the functions all doing? They're all going to what? Are they going to ever stop growing? So therefore, the answer to that question then would be infinity. Okay, and the limit as x approaches negative infinity for these functions. Okay, as we approach negative infinity, as we go off to the left, we said they get closer and closer to what number? 0. Okay, they get closer and closer to the x-axis, so therefore that question then would be 0. Okay. Now, if we change the bases and instead make the bases fractions, we mentioned earlier that we're going to get decay functions. And I'm just going to look at one of these, but we can see that really what happens is we get the same shape, but it's ultimately just a reflection over the y-axis, isn't it? Okay. So anytime that we have that base that is a fraction, something less than 1, we're going to get a decay function, which ultimately means is going to have very similar properties to the growth functions. Okay? Same domain, same range, flip-flop on the increasing and decreasing, same continuity, also flip-flop on the limits at infinity and negative infinity, because we're going up as we go to the left, down as we go to the right. So again, this type of function occurs when we have a fraction base, like 1/2 or 3/4 or 1/3. Okay, any kind of base that's less than 1, we're going to get a decay function, again with similar behavior, okay, but opposite in some cases because we're going the other way. Ultimately, it's just a reflection of the 2 to the x function over the line y equals x. Or, excuse me, over the line x equals 0, over the y-axis. I want you to think about why that's the case, too. If I had y equals 2 to the x, we just saw what that looked like. Okay. Earlier, we talked about the fact that if I have 1/2 to the x, okay, that's really the same as 2 to the negative x. Okay. And think about what we know about transformations. If I have 2 to the x and I have 2 to the negative x, what does making a negative x do to the graph of 2 to the x? It flips it over the y-axis, doesn't it? Okay, that was one of our properties that we learned about when we did transformations. Okay, so not surprising, these two are interchangeable. And remember, the reason is we can write that as 2 to the negative 1 to the x, and of course, that's the same as 1/2 x. Okay, so there's two things that are going to generate decay functions. One, by having a base that is less than 1, or 2, by having a base that's greater than 1, but having a negative x. That negative x is going to indicate also a decay function as well.